Today, let's talk about the research progress of cathode materials for sodium-ion batteries. Why are sodium-ion batteries so popular? Because they are rich in resources and low in price, and have become a favorite in the field of energy storage. However, the large ionic radius and slow kinetic rate of sodium ions pose challenges in finding suitable sodium storage materials. Especially, the development of high-performance cathode materials for sodium intercalation is crucial. First, let's see why sodium-ion batteries have attracted attention. The energy and environmental problems are severe. Fossil fuels are depleting rapidly and causing environmental pollution. Although renewable energy is good, it has regional and intermittent problems. Electrochemical energy storage has become the key. Lithium-ion batteries are widely used, but due to the shortage of lithium resources and the rising price, they cannot support both the electric vehicle and large-scale energy storage industries. Sodium-ion batteries are different. Sodium ranks 6th in the content of the Earth's crust, is rich in resources, has similar electrochemical properties to lithium-ion batteries, and has a cost advantage. The negative electrode can use aluminum instead of copper as the current collector, so it has broad prospects. Next, let's talk about the development of cathode materials for sodium-ion batteries. The research on sodium storage electrodes began as early as the 1970s, almost at the same time as the research on lithium storage materials. In the early stage, the research mainly focused on transition metal oxide material systems. For example, in 1980, there were reports on the sodium storage performance of related materials. However, after 1990, with the practical application of lithium-ion batteries, the research on sodium-ion batteries stagnated for 20 years. In recent years, due to the high demand for energy storage batteries in new energy, sodium-ion batteries have been paid attention to again. The cathode materials include transition metal oxides, polyanionic materials, Prussian blue materials, organic compounds and polymers, amorphous materials, etc. First, let's talk about transition metal oxide materials, which are represented by CnaeBattery and can be divided into tunnel oxides and layered oxides. When the sodium content is high, it is mostly a layered structure, with structures such as O3, P3, O2, and P2. The electrochemical performance of different structures is affected by the phase structure, and there are phase transformation problems that affect the cycle performance. The O3 structure has a high capacity, and the P2 structure has a high ionic conductivity. The research mainly focuses on element doping and substitution to stabilize the structure. When the sodium content is low, it is mainly a three-dimensional tunnel structure oxide, which has stable performance but a low initial charging capacity. Polyanionic compounds generally have a stable framework, good cycling performance and high safety, and can also regulate electrochemical properties. However, they have low electronic conductivity and volumetric energy density. Among them, the electrochemical performances of phosphates, pyrophosphates, and sulfates are relatively prominent. The common composition of Prussian blue compounds is in a face-centered cubic structure. Alkali metal ions can be inserted into and extracted from it. Different transition metal ions can be selected to obtain different sodium storage performances. Organic compound cathode materials have a high theoretical specific capacity. Rich raw materials are environmentally friendly, low in price, and have flexible structural design. Organic small molecules such as quinones, anhydrides, and polymers are research hotspots. Amorphous compounds have a long-range disordered and short-range ordered atomic arrangement. Sodium ions react on the particle surface, so they have good stability. However, it is more difficult for cathode materials to form an amorphous phase. That's all for today's science popularization. See you next time.